to make this happen, chemists don't just wing it. There's a really clear game plan. You can't just throw things in a beaker and hope for the best. It's a very precise, two-part strategy. So let's take a look at the chemical blueprint for this whole process. Here it is, our roadmap. It's really just two main stages. First, we've got something called diazotation. That's all about getting our first key ingredient ready to go. Then we have azocoupling, and that's where we make the final connection, where the magic happens. Diazotation, then azocoupling. That's the core of it.
All right, let's dive into Act 1, diazotization. This whole step is about one thing: taking our starting molecule, a chemical called aniline, and basically prepping it for the main event. We have to activate it, make it ready to react.
So here's the deal. Aniline by itself is actually pretty chill, pretty stable. It's not just going to up and decide to form a dye, so the whole point of this first step is to turn it into this super energetic, highly reactive molecule that is just desperate to bond with something else.
So how do we pull off that transformation? Well, we need a special attacker, a kind of chemical secret weapon, and it's called the nitrosonium ion. The cool thing is, we make it right there in the flask, on the spot, by mixing sodium nitrite and hydrochloric acid. This little guy is our electrophile. It's what kicks this whole reaction into gear. And here's the before and after of step 1. On the left, you see what we started with, our aniline and a couple of other things. Then, after that nitrosonium ion does its job, bam! On the right, we've got our super reactive star for Act 2, benzene diazonium chloride. Mission accomplished. Molecule 1 is officially activated.
Okay, on to Act 2. This is the azocoupling. Our first molecule is ready, it's reactive, but it needs a dance partner. This is the moment we've been waiting for. It's where the two main pieces finally come together and that beautiful color is born.
So who's the second key player? It's a molecule called 2-naphthol. And just like our first molecule, it needs a little prep. We give it a bath in a sodium hydroxide solution, which makes it electron-rich. You can think of it like charging a battery. We're loading it up with energy, making it super attractive to that diazonium ion we just made. And this, right here, is the climax. This quote just nails it. Our charged-up 2-naphthol finds that super reactive diazonium ion from step 1, and it doesn't just casually float by. No, it attacks it, going in to form a brand new stable bond. This is the moment of connection. And the result of that epic attack? It's this right here, the azo bond. See that nitrogen double bonded to another nitrogen? That little bit of structure is the absolute heart of the dye. It's what scientists call a chromophore, which is just a fancy way of saying it's the part of the molecule that's responsible for color. It soaks up some light, reflects the rest, and what we see is that amazing orange-red. That bond is the color. Okay, so that's the theory, right? We've talked about what's happening on a tiny molecular level. But what does this actually look like in a real lab? How do you physically do this? Let's shift gears from the theory to the actual lab bench procedure. So here's the step-by-step recipe. It's all about precision. First, you get your aniline solution ready in some acid and get it really cold. Then, in a separate beaker, you get your 2-naphthol solution ready. Once both are prepared and ice cold, you very slowly mix them together. And just like that, you'll see this brilliant orange-red solid, the dye, just appear and fall out of the solution. After that, it's just a matter of filtering it, giving it a rinse, and letting it dry. Now listen up, because if there is one thing you absolutely have to remember from the practical side, it's this number, 0 to 5 degrees Celsius. The entire reaction has to be kept ice cold, and here's why. That benzene diazonium chloride we made back in step 1, it's super unstable. If it gets even a little bit warm, it just decomposes, it falls apart, and your whole experiment is a bust. Seriously, temperature control is everything here. Okay, so we've covered the theory, we've walked through the practical steps in the lab. Let's kind of zoom out now and lock in the big picture. What are the main takeaways from all this? All right, here are the key principles, the 4 things you really need to know. First, diazotization makes our first molecule super reactive. Second, azocoupling is where that reactive piece joins up with its electron-rich partner. Third, that azo bond, the N double bond N, that's the part that actually creates the color. And finally, number 4, you gotta keep it cold or it just won't work. That's the whole story in a nutshell. And that brings us to a final, really cool question. We followed this exact recipe, right? And we got this specific orange-red color. But what if you swapped out the starting materials?
What if you made just a tiny little tweak to one of those molecules? Could you unlock a whole rainbow of other colors? Yellows, blues, purples? The answer is yes, and that's the real beauty of dye chemistry. It's something to think about. Thanks so much for joining me.